Imagine a future where technology lets you fly a spaceship at light speed. Inside the ship, you raise a mirror. Would your reflection appear at all? Could you see yourself in it? When we look in the mirror, light from our face hits the mirror and reflects to our eyes. But if a spaceship moves at light speed, the mirror moves forward at the same speed, so the light from your face can't catch up to the mirror. From this view, you see nothing in the mirror. However, some think this explanation is wrong because the spaceship travels at light speed, and everything inside, including light, has inertia. So, the light on your face should move at the spaceship's speed plus light speed, allowing it to reflect off the mirror, letting you see yourself. Which of these two explanations do you think is correct? At first, you saw it or you didn't. Even without testing yourself, the outcome was binary. So you had a sense, but someone ran an experiment that broke both explanations. To avoid inertia affecting light, he aimed a fixed laser at a car's light speed meter. If the car moved forward, its relative speed to light dropped, so the reading fell. Moving backward increased relative speed, so the reading rose. Yet in real tests, however the car moved, the reading stayed unchanged. Even when both light source and car were moving, the result was surprisingly the same. Scientists have conducted countless precise experiments and concluded that light speed is constant for any object. This is the principle of the constancy of the speed of light in special relativity. Just how absurd is this conclusion? In short, if I'm outside the ship watching you chase light at 99.9% of light speed, I'd still measure light. Of course, at 300,000 km/s, it's only 0.1% faster than you. But from inside the ship, you'd also see light racing away at 300,000 km/s, not merely 0.1% faster. So why do our observations conflict? In a minute, you'll understand why. You're on a truck, looking in a mirror, while I'm watching from a roadside tower. From your view, when you turn on a laser pointer, the beam goes to the mirror and reflects back to you. But for me on the tower, because the truck is moving forward, the actual path of the light that I see looks like this. I see the laser travels farther than you see. And previous experiments show that the speed of light is the same for us. With speed constant and distance longer, it means I spend more time than you, so your time slowed. This is the time dilation effect caused by motion. If you're curious, middle school Pythagorean theorem suffices to easily compute time dilation. And often, premium ingredients need only the simplest, most basic cooking. If you calculate it and then verify it, you'll find that it doesn't add up. Imagine a ship racing light at half light speed to a point 300,000 kilometers away. I see the light take 1 second and the ship too. But time dilation slows your onboard clock, so you experience only 1.7 seconds arriving. Here's the problem. 1.7 seconds times half light speed means you traveled only about 260,000 kilometers from start to destination. So why did I see you travel 300,000 kilometers, but your ship shows only 260,000? This is the length contraction effect, because motion affects not only time, but also space. At rest, the gap is 300,000 kilometers. The instant you accelerate to 0.5 c, before you move, you see the universe flatten, shrinking your distance to the target to 260,000 kilometers. From my view, universe unchanged. You suddenly look flatter. Faster means flatter. So as a guy, you must understand length contraction and time dilation because they clearly show that time and length are relative, so there's no reason not to be confident. Back to the video's title. What happens if you look in a mirror on a lightspeed ship? If the spaceship is heading to the Andromeda Galaxy 2.54 million light years away, it would take 2.54 million years to reach it from Earth. For you, when the ship hits light speed, length contraction and time dilation peak. From your view, the universe flattens to a two-dimensional plane. Distance and time vanish. You instantly reach Andromeda. Don't stop now. Return to Earth at light speed. When you arrive, your parents are 5.08 million years old, but you're still as young as when you left. So the best thing to do right now is to call home and say hello. In summary, since the spaceship travels at light speed without using time, the issue of seeing yourself in a mirror doesn't exist. Like asking if the answer is yes or no, but the answer is no. Why isn't time involved? Ultimately, because light speed is constant. So then why is light speed actually constant? I don't know. Nobody in the solar system does, but it won't stop us exploring the universe. The author of the special theory of relativity is Einstein, but few people know that he was very passionate about sailing and once owned 2 sailboats. He said, "A ship is safest in harbor, but that is not what ships are built for."